Hello, everybody, and welcome to Alex Derives Stuff. Today's derivation is going to be on Archimedes' death ray. More specifically, we're going to derive the focal property of parabolas, and we're going to use some vector stuff to do it. Now, you might wonder, very reasonable question in this case, is, all right, so what's the focal property of a parabola, and what does it have to do with Archimedes and death and rays? So here's the idea. Suppose I have a parabola. Here's roughly a parabola, and we've got some light source that's very far away that's shining directly into the parabola. So we've got a bunch of light rays coming in all from the same direction, sort of perpendicular to the axis of the parabola, which later on we will call the y-axis. These parabolas have a very neat property, which is that there's a point called the focus where if I look at one of these light rays, it comes in this direction, bounces off, and then goes through this point. And the cool thing about this is that if I draw multiple light rays and where they come in and where they reflect, they all go through this same point called the focus. Okay, and so you can see there roughly that's what's going on. And a parabola is very special. It's one of the only shapes that does this. Actually, it's the only shape that does this. Okay, so that's what we're going to derive, the fact that these reflected rays actually all go through the same point. Now, what does this have to do with Archimedes and death? Well, you can imagine if I had a very wide parabola, so say something like this. There we go. There's a very wide parabola. The focus might be like up here somewhere, and then all the light rays that come in would bounce off of it and from very far away, like the sun, and they would all go through this focus. And so if I have a whole bunch of light rays that come in and and then they all go through the same point, then what happens is that point heats up. It becomes very, very hot, and things will light on fire if they get too hot. It's a matter of legend if you Google this as to whether or not Archimedes actually built one of these, but there were, in his time, practical applications to this. For instance, that's how you get a lighthouse light. That's how somebody built the lighthouse light in Alexandria. Now in 3D, what you'd get is you can imagine a bunch of these parabolas sort of rotated around each other. So if you have a paraboloid with a circular cross section, then you get a 3D version of this. So light rays come in, bounce off the top or bounce off the sides, go through the focus, and and all of them superheat this spot. Okay. On the flip side, you could have a light source at the focus and it'll go in the reverse direction and you'll get sort of a straight ray out. And that's the whole lighthouse business. Okay, so we're going to need some background things in order to do this. So one bit of background is the notion of vector projection. So if we have two vectors and I want to find the projection of one onto the other, apparently this formula is how you do it. And I could direct you to some separate locations where I have a derivation of this. But basically the idea is that, all right, well, suppose I've got some vector, there's v, and then here's some other vector, which I'm calling n for some reason, and actually you'll see why. And then the projection of v onto n would just be like, well, I want to know how much v points in the n direction. So I make a right triangle here. And this p vector is the projection of v onto n. Now, a special case of this is if this n happens to be a unit vector. So if you notice, I've got this n dot n. This is an annoying fraction right here. So I've got this n dot n on the denominator. So if the n happens to be rescaled so that it's unit length, and this formula simplifies quite a bit, right? And then because the n dot n happens to be 1. So our normal vector, well, our n vector, whatever it is, or later on we're going to call it a normal vector. Well, that's, we could do this as long as we make it unit length first. Okay. Another thing that we're going to have to know about is how to find a normal vector to a curve, specifically a parabola. And so this little theorem right here is if we've got a curve in the form f of xy equals c, and if we know what point that lies on this curve, then we can calculate a normal vector by computing the gradient and plugging in our point. Now, the trick here is that whatever our curve is, we have to write it in a form where all of the x's and y's are on the same side. So what is a normal vector to a curve? Well, imagine we've got some sort of curve like this, and then I've got some point. A normal vector could point that way. It could also point in the opposite direction. So minus n, right? No, it's just perpendicular to the curve. If you imagine drawing a tangent line, it's like a vector that's perpendicular to the tangent line. So this is tangent. That's the line that just kisses the curve at that point. And then the normal would be just whatever direction is perpendicular to that. And we tend to have two choices, and it sort of depends on how we set up our f of xy. All right. Now, let's get started with all of this stuff. So one first thing we need to do is talk about the law of reflection. So what does a light ray do when it reflects off a surface? Okay, well, you may have heard this before. The incident angle is the same thing as the reflected angle. All right, so what does this mean? Well, if we've got some sort of flat, we'll do a flat surface for the moment, but this works just as well for curved surfaces. So if we have some kind of flat surface, here's a flat surface. And if we've got, so this flat surface would have some unique direction, well, one of two directions that's perpendicular to it. So we can call this, I will call it n hat to just make it automatically a unit vector. So the little hat sort of denotes that it's unit length. And if we have an incoming ray, so we have an incident light ray, this angle that the incident ray makes with n, call it theta, I guess. I don't know why theta is just always the letter that people use for angles, but whatever. All right, this incident ray makes a certain angle with the normal, and so we'll call this incident ray, say v, and I'll make that a unit vector too. We can always rescale these to make them whatever length we want. And what we would like to, this reflects off, and the law of reflection, so we'll call our w hat here, we'll call this our reflected ray. And the law of reflection just says, like, well, okay, we get the same angle with the normal on either side with the incident ray and the reflected ray. Okay, hopefully that's pretty intuitive. You could practice this with a mirror or whatever. Okay, now what we want to do is we want to recast this law in terms of vectors. So and then we can do this without actually using the angle theta. So what we can do is use vector projection to come up with a formula. So for W, our reflected ray, to find W in terms of the incident ray and the normal vector. And then I'm sort of arbitrarily making these all unit vectors. We don't have to do this. It just makes the derivation come out a little bit nicer if we make them unit vectors first. Okay. Well, how do we do this? Well, vector projection to the rescue. So one thing is rather than using the incoming ray, I'd like to flip the direction of that. That'll make all of this vector projection a little bit easier. So let's flip V. And so we'll say, here's our surface. Then here's our normal, our unit normal. And so if we flip V, and so we say like, okay, so here's, say, minus V, this vector. Okay. And we can split minus V into the sum of two vectors, one that points with n, and one that points perpendicular to n. So I will call the one that points parallel, the normal component here, I'll call that P, and I'll call this other one Q. Okay, cool. So what are these things? Well, this P is just the straight up vector projection of negative V, so negative V hat, onto our normal vector. Okay, so we get then a formula for that, right? Our P is equal to, well, negative V hat dotted with n times n, right? Because again, that's this formula where because the n is a unit normal vector, we can use this sort of shortened formula. Okay. Now, what's the Q? Well, by vector addition, we could see that P plus Q is equal to negative V, right? So P, if I go in the P direction, then I go in the Q direction, the result is negative V. So if I solve for Q, because I already know the other two, so then the Q would be minus V minus P. Okay, so our Q plugging into here, so it would be minus our V hat. So if I subtract our P, that would just flip the sign on this negative here. So that'd be plus V dot N times N. Okay, so now how do we get from here to our reflected ray? So our reflected ray, well, it makes the same angle. So our W hat right here. So if we split it up into the same components right here, we could sort of say that, well, what's this vector right here? So the P would be the same. That would be the same perpendicular component because I've sort of scaled this so it's the same length. And then, well, this purple vector here is just the opposite of Q. It's the same length and it points in the opposite direction. So this would be minus Q. So here our W would be P minus Q. Oh, okay. So our reflected ray, so our reflected vector, I should say. We'll get to how to get from a vector to a ray is, so it would be W is equal to P minus Q. And we could just plug right into here. So we could say W is, so let's see here. So P, so this is minus V dot N times N minus Q. So if I subtract Q, that would be plus V. And then minus that other thing. So minus V dot N times N. And then cleaning this up a little bit, we get an expression for our reflected vector. So we get our W, I guess it would be W hat. This also works out to be a unit vector, as you can work that out. So we have a positive V, and then minus 2 of these projections. So minus 2 V dot N times N. So this is what we're going to work with right here. This is the direction that the reflected ray points. Okay, now if we also have a point that, so we also have like the actual point of contact, we can sort of parameterize this as whatever that point is plus W times T. Okay, so now to parabolas. So now let's take a look at our parabolas. So suppose we have a parabola. So we have a parabola. What just happened here? So we'll just say it's y equals some constant times x squared, where that constant a is positive. All right, so I'll draw some axes here. X, y, and I'll draw a parabola here. I'll make it purple for parabola. So there's a sort of generic parabola. All right, yeah, and then we'll have some particular point here, say x naught, and a times x naught would be a times x naught squared would be the y value there, right? And we've got an incoming light ray. So an incoming light ray that's vertical, right? So that was the setup of the problem, is they come in perpendicular to the axis of the thing. And then we're going to have some reflected ray. We'll call that W. So we say that's W. And what we're after is this point right here. We're after like where this reflected ray intersects the y-axis. And so the claim is that no matter what this x naught is, so if I try this at any different point on the parabola, as long as the incoming ray is vertical, then I'll always get the same point where the reflected rays will always intersect the y-axis at the same point. So let's see here. So first things first, what's this v? So v is the direction of the incident light ray. Okay, so v would just be, well, 0, -1, right? Is this pointing straight down? Okay. Oh, we need to find the normal vector. Okay, so how do we find the normal vector to the parabola at the point? I guess it would be x naught comma a x naught squared, right? So whatever this x naught is. Well, let's see here. This is where our gradient stuff comes in. So if we take a look at the curve y equals ax squared, we can rearrange this so that it's like y minus ax squared equals 0. There's lots of other ways of rearranging it. This, I would suggest, is the easiest. And so we can think of this as a level curve of the function f of xy equals just y minus ax squared. And so if I compute the gradient of this function and plug in our point right here, then that'll give me a normal vector at that point. So let's see here. So what's the gradient of this? So the gradient of f of xy, well, so derivative with respect to x would be -2ax. Derivative with respect to y would just be 1. Cool. And so if we plug in our point, I guess that just means replace the x with whatever this particular x coordinate is, x naught. So the gradient of f at the point x naught a x naught squared would be -2a x naught comma 1. Now, all of the stuff I was previously looking at was, well, we wanted a unit normal vector. So this is a normal vector. So we want to make it unit length so we can use all our formulas that I had derived earlier. So let's normalize the normal vector. And in order to normalize it, what the heck just happened? In order to normalize it, we just divide it by its own length. So the length of this, the magnitude of the gradient at this point, would be square root of the first thing squared plus the second sort of thing squared. So first thing squared would be 4a squared x naught squared plus second thing squared would be 1. So our unit normal at that particular point would be, we'll call this n hat. It's this stuff divided by the magnitude, right? So it'd be, got to do a bigger bracket here. So -2a x naught over the square root of 4a squared x naught squared plus 1, comma 1 over that same doodad, root 4a squared x naught squared plus 1, end bracket. So that is our unit normal vector at some point for the parabola. Okay, cool. So we got that. If I draw that on here, we'd have, what color should I use? I'll use blue. So here we'd have some sort of unit normal vector. Cool. I'm assuming that's of length 1. I have no idea. But all right. And so you can see very roughly here that according to my cartoon, very roughly like V and W sort of make the same angle with N. All right, so now we need to find the vector W. So we need to find the direction the reflected ray points, and that's where we can use our formula. Now that we have the direction of the incoming ray, and we have the direction of the normal vector, so let's do that. So the direction the reflected ray points was W equals, what was it? Let me scroll all the way up here. V minus 2 V dot N times N. Okay. So V minus 2 V dot N times N. Now, quick point of thing. I guess technically, according to my derivation, it didn't matter whether V was a normal vector or not, or was a unit vector or not. But as it happens, we chose a V that was one, right? So for us, the V was 0, -1, and the N is this doodad up here. And so our N is minus 2ax naught over that square root imajigger. 4a squared x naught squared plus 1, comma 1 over root 4a squared x naught squared plus 1. All right, so all right, I don't necessarily want to plug in whole hog here, so let's at least do this dot product first. So let's compute v dot n. So v dot n, well, if I do the dot product of these two things, it's 0 times the first thing. Okay, so 0, and then minus 1 times the second thing. So we just get minus 1 over root 4a squared x naught squared plus 1. And so that's what we would like shove into the parentheses here. And we're going to multiply it by -2. Okay. And then we're going to multiply that by our n. So we then have our w would be our v, so 0, -1. So minus 2 times this thing, so plus 2 over that junk. So plus 2 over root 4a squared x naught squared plus 1 times our unit normal. So times minus 2a x naught over square root doodad, comma 1 over square root doodad. Sweet. Now, all right, so we can clean this up a little bit more. And so one thing we probably want to do is distribute all of this stuff. Hey, that'll lift the roof off of that square root. So we got W equals 0 minus 1 plus, so if I distribute this constant into the first component of this vector, I guess this would be minus 4 a x naught. What just happened here? Tablet's going crazy. There we go. So minus 4a x naught over, and then like the square root thing times the square root thing is just the thing under the square root. So 4a squared x naught squared plus 1, comma, and then 2 over that junk without the square root. So 4a squared x naught squared plus 1. Right on. And oh, okay, so we can then combine these two. So 0 plus, so our W would be 0 plus the first thing would be the first thing. So just minus 4a x naught over 4a squared x naught squared plus 1, comma, this junk minus 1, right? So -1 plus 2 over that stuff. So 2 over 4a squared x naught squared plus 1 minus 1. And one last bit of simplification here. I can't help myself. Let's get a common denominator here for this thingamajig in the y component of w. So w hat would be, so I'm not going to mess with the first thing, minus 4a x naught divided by 4a squared x naught squared plus 1. And then if I get a common denominator, it's 2, I guess the common denominator would be 4a squared x naught squared plus 1. So it's 2 minus all of that junk on the denominator would be our new numerator. So the 2 minus 1 would give me a 1, and then minus 4a squared x naught squared. And then all divided by the same thing. Cool. So this is the direction that our reflected ray would point at a particular time, or at a particular location on the parabola. So, okay, now fun exercise, verify that this is in fact a unit vector. So my putting the hat instead of an arrow is justified. But okay, so now let's go back to what we were trying to prove in the first place. Where was our parabola? Our parabolas at the very beginning. So the idea was that these guys should all of these light rays that come in vertically that hit the parabola at any point, or x naught is just whatever x coordinate it hits the parabola at, those should all meet at some particular point. Now, I claim it's going to be on the y-axis. You could have like symmetry reasons for that. So what we need then is the equation of this line right here. And we could do it in y equals mx plus b form, or for me, it's easier to do it, since we have vectors and stuff, we could do it in parametric form. So here's the reflected ray. And one thing you might notice here is the vector that we use for the reflected ray doesn't have to be like the unit vector w. It could be any scalar multiple of that. Or I guess to get the correct direction, we need any positive scalar multiple of w. Okay, so let's rescale w so it looks nicer. So notice if we multiply everything by that junk on the denominator, it still points in the same direction. So we'll rescale w so it is easier to algebra. All right, let's do that. So our new w, I'll call this just regular w with the arrow, and I'll basically just get rid of those denominators. Minus 4a x naught, comma, 1 minus 4a squared x naught squared. All right. This points in the same direction as our original w. I guess it's longer, right? Because definitely that denominator is bigger than 1, so we multiplied by a number that was bigger than 1. Okay, so now we want the reflected ray is the line that points in the direction of w and goes through the point x naught, comma, a x naught squared, right? Like that's the point where that light ray bounces off of the parabola. Oh, okay. So we could write a parametric equation for this. So we could call this like r of t for reflected, I guess. So that would just be our point, x naught, comma, a x naught squared, plus our vector. So plus negative 4a x naught, comma, 1 minus 4a squared x naught squared times t. And then if we want, here's what I'll do. I'll just write the x and y coordinates separately. So like the x coordinate of this would be x naught, and then minus 4a x naught times t, right? It's the x naught plus that thing times t. And then the y coordinate would be ax naught squared, right? So there's the y coordinate there, plus this thing times t. So 1 minus 4a squared x naught squared times t. Okay, so remember, my claim was that no matter what x naught is, this will have the same y-intercept. So the y-intercept will be, okay, well, what's the y-coordinate when x is equal to 0 for this line? All right, well, let's see here. So let's find the y-intercept. So the way we could do that is just set x equal to 0. And then if we do that, we can solve for the t value that makes x equal to 0. So we do 0 equals x naught minus 4a x naught t. I guess we can assume that the x naught is not 0, and we already assumed that the a isn't 0. Okay, so that if we solve for t, t is equal to 1 over 4a. Now, if we plug this t value back into our y, so then we get y would be a x naught squared plus 1 minus 4a squared x naught squared times 1 over 4a. And if we clean this up a bit, what we'll find is that all of the x naughts will cancel out. So we'll get y equals a x naught squared plus, so if I distribute this 1 over 4a, I get 1 over 4a minus, so if I do 1 over 4a times this second term in the parentheses here, the 4's cancel, and one of the a's canceled. So we're just left with a x naught squared. Those cancel, and we're left with the y-intercept is 1 over 4a. And now here's the point here. This y-coordinate for the y-intercept of our reflected ray does not depend on x naught, right? So in other words, this is the y-coordinate of the y-intercept of the reflected ray, no matter where the incoming ray came from. Okay, so our result is that every incoming light ray, every incoming vertical light ray reflects off the parabola at some point and passes through the point x equals 0, y equals 1 over 4a. Okay, so in other words, yeah, every incoming vertical light ray reflects off, goes through the same point, and then this is the focus of the parabola. And in principle, if you can get enough light rays to focus at the same point, you can light anything on fire that passes through that point. Archimedes' death ray. I hope everybody enjoyed that. I certainly did. Hopefully, I will have more derivations for you soon.